Hey, so we hear all the time about building AI models, right? But the real magic, the secret sauce, isn't just in the architecture. It's in actually teaching them. Today, we're going to pull back the curtain and really get into the nitty-gritty of the training process, step by step.
Okay, let's just dive right in. This is the big question, isn't it? We're going to tackle this head-on by looking at the core ideas that take, a digital blank slate and turn it into a smart decision-making machine. So, this is where we start. Picture a brand new neural network. It literally knows nothing. Its internal settings, which we call weights, are totally random. So if you ask it a question, you're just going to get a wild guess back. The whole goal here is to basically walk it through a school of data so it can finally start making some smart predictions. All right, first things first, we've got to understand the tools the model actually uses to think. And deep inside every single neuron, there's a tiny but super important decision maker.
And this is that decision maker, the activation function. It's really just a little math gate that checks out the incoming signal and decides, hey, is this important enough to pass along to the next layer of neurons? This is absolutely crucial. Seriously, without these things, a network couldn't learn any complex patterns at all.
And this is the perfect way to think about it. It's not just a simple on or off switch. It's much more like a dimmer switch in your house. A really weak signal, yeah, that might get ignored, the light stays off. But a strong signal gets passed on with confidence. The light turns on brightly. The function decides how strongly to crank up that light for the next neuron down the line.
And the beautiful part is when you actually go to write the code, this entire concept just boils down to one simple little argument. Right here, we're just telling a layer of neurons what kind of decision maker to use. It's a really elegant way to handle a pretty complex idea.
Okay, so now we know how a single neuron kind of thinks. Let's zoom out a bit. You can think of the whole training process like a game, and this game has a really clear objective. Get the best score you possibly can. But how do we actually keep score? Well, the loss function is the scoreboard. Every single time the model makes a prediction, the loss function compares it to the right answer and spits out a score. A really high score means it was way, way off. A low score means it was getting close. So the whole point of the game is to get this wrongness score as close to zero as you can. The dartboard analogy is just perfect for this. Every prediction is like throwing a dart at the board. The loss, that's just the distance from where your dart landed to the bullseye. A huge loss means you miss the board completely. A tiny loss means you're getting really, really close to that perfect score. Okay, so if the loss function is our scoreboard, then the optimizer is the coach. It's the navigator. It looks at that high score and says, all right, that was a bad throw. Let's try adjusting your aim this much and in that direction. It's the thing that actually guides the learning and makes the adjustments. This gives us a really great mental picture of how an optimizer works. Imagine you're blindfolded, standing on a mountain. That mountaintop represents a high loss score. Your goal is to get to the lowest point in the valley. You can't see the path, right? But you can feel the slope of the ground with your feet. Well, the optimizer does the exact same thing, just with math. It finds the steepest downhill direction and takes a step. That's the core idea right there. So these two things, the loss and the optimizer, they work together in this constant feedback loop. The model makes a guess, the loss function scores it, the optimizer adjusts the model's internal wiring to do a little better, and then the whole cycle just repeats, thousands, sometimes millions of times, getting a tiny bit smarter with every single pass.
Now this is a really critical tuning knob for our blindfolded hiker. The size of the step the optimizer takes down that mountain is called the learning rate. So the question is, how big should that step be?
And finding the right balance here is, well, it's kind of an art and a science. If the learning rate is way too high, you're taking these giant leaps, and you might just jump clear over the valley and land on the next mountain over. But if it's too low, you're taking these tiny, tiny baby steps, and it could take forever to get to the bottom. Nailing this is a core challenge in training a model well. Okay, so we get how the model learns from its mistakes. But what about the logistics of it all? A model doesn't just look at millions of data points all at once. I mean, that would be totally overwhelming. No, it has a study plan.
So instead of just drowning the model with the entire data set, we feed it data in small, manageable chunks. And these chunks are called batches. The model looks at one batch, learns what it can, and only then does it update its internal weights.
The flashcard analogy is just perfect. You wouldn't try to memorize 1,000 flashcards in one sitting, right? You'd study a small stack, maybe 32 of them, see which ones you messed up, learn from those mistakes, and then you'd move on to the next stack.
That is exactly how batching works for a neural network.
And once the model has gone through every single one of those little batches of flashcards, once it has seen the entire dataset just one time, that complete pass is what we call an epoch.
Think about it like studying for a big test. Reading the whole textbook one time is almost never enough to really master the material. You need repetition, so we train models for many epochs, 10, 20, sometimes hundreds, letting it see the same data over and over to really let the lesson sink in.
So the model is off in its own little world. It's working hard, trying to get its mathematical loss score as low as possible. But how do we, the humans running the show, actually know if it's doing a good job in a way that makes sense to us?
This slide clears up a super common point of confusion. The loss, that's for the machine. It's a complex mathematical value that the optimizer needs to figure out its adjustments. But metrics, like accuracy, those are for us. We just want to know in plain English, hey, what percentage of questions did the model get right? The loss is how it trains. The metric tells us the final result.
And what's amazing is that this entire complex process we've just walked through, it's all controlled by just two simple lines of code. That first line, compile, that's where you set the rules of the game. You define the loss function, the optimizer, and the human-friendly metrics. Then that second line, fit, that's what kicks the whole learning loop into gear, telling the model what data to study and for how long. It's an incredibly powerful summary of everything.
So, to wrap it all up, we've basically defined the game for our machine. Get that loss score down. We gave it a coach to guide it, the optimizer. We set up its study schedule with epochs and batches. And finally, we created a human-readable report card using metrics so we can actually see how well it's doing.
You know, this fundamental process, this whole loop of predicting, scoring, and adjusting, this is the engine that drives everything from recognizing your face in a photo to translating languages in real time. It really makes you wonder, now that you know the recipe, what's the first thing you would teach a machine to do?